In this video, we're going to learn how to multiply binomial radical expressions. Now, when you have two binomials being multiplied, you can approach it very similar to the FOIL method. So we'll first multiply our first term, so 4 times 5, which is 20. 4 times 4 square roots of 2, which should be 16 square roots of 2. You'll multiply what's outside the radicals to each other, and just keep what's inside the radicals multiplied to each other. Then we'll do our inner, so 2 square roots of 2 times 5 gives me 10 square roots of 2. And then when I do 2 square roots of 2 times 4 square roots of 2, I'll do 4 times 2, 2 times 4, which is 8, square roots of 2 times 2, since those are the radicand underneath the radical, and that gives me 4 underneath the radical. Now, what I can do is simplify everything. So I have 20, 16 square roots of 2, and 10 square roots of 2, giving me 26 square roots of 2. And then 8 times the square root of 4, which is 8 times 2, which is 16. And now I can add the 20 plus that 16 to give me 36 plus 26 square roots of 2, which I cannot simplify any further since that's 2 is not a perfect square. But now I have the 1 plus the square root of 72 times 5 times the square root of 2. Now I'm seeing here that the 72 is quite large, but 72 does have a perfect square in it. So usually when you can, it's better to simplify before you multiply to make the numbers a lot easier to handle. So the square root of 72 is the same as 36 times 2. And since 36 is a perfect square within 72, I can now take the square root of 36 and get 1 plus 6 square roots of 2 times 5 plus the square root of 2. And now I'm ready to FOIL and get my new binomial expression afterwards. Because when I multiply, I'll have 1 times 5, which is 5, 1 times the square root of 2, which is the square root of 2, 6 square roots of 2 times 5, which is 30 square roots of 2, and then 6 square roots of 2 times the square root of 2, which should be 6 times an understood 1, so just 6, times the square root of 4, which is 2. Now simplifying, I have 5 plus square root of 2 times 30 square roots of 2 is 31 square roots of 2 plus 12, since I have 6 times 2 going on there with the square root of 4. And then 5 plus 12 is 17 plus 31 square roots of 2. Now going further, sometimes you'll get the same binomial squared, which means that you multiply it by itself. What I mean by itself is not alone, just take the same exact binomial expression and put it right next to it so you can treat it the same as you would before. Now multiplying, you have the square root of 3 times the square root of 3, which is the square root of 3 squared, because it's the same exact thing. And then we have outer minus the square root of 15. And then negative square root of 5 times the square root of 3 is also a negative square root of 15. And then negative square root of 5 times negative square root of 5 is plus the square root of 5 squared. This gives me the square root of 3 squared minus 2 square roots of 15 plus the square root of 5 squared. Now the square root of 3 squared, the square root and the square can cancel, leaving me with 3 minus 2 square roots of 15 plus 5. And then I'll get 8 minus 2 square roots of 15. Now the reason why I wrote it this way, rather than combining the radicals, is this situation is known as a perfect square trinomial, because it comes from my binomial being squared. So we can actually use the idea for a perfect square trinomial to help us multiply these out. That's when you have a plus b is squared is equal to a squared plus 2ab plus b squared. And what you're seeing here now, if I compare it, is the square root of 3 squared plus 2ab. But here I have a minus 2. That's because the a and the b here is 3 and negative square root of 5. That would create a negative square root of 15. So 2 of those plus the square root of 5 squared, the second term. So when I look at this expression, before I start, just like before, I can simplify both the square root of 12 and the square root of 72, so I will do that. The square root of 12 can be rewritten as 4 times 3, which is 2 square roots of 3, plus square root of 72, which we discussed earlier as 36 times 2, can be written as 6 square roots of 2. And now I'm going to just use that perfect square trinomial to multiply this out. So I'll have 2 square roots of 3 squared plus 2 times 2 square roots of 3 times 6 square roots of 2, and then plus 6 square roots of 2 squared. Just using that perfect square trinomial. And if you don't like this method, just write them side by side next to each other and FOIL it out. It will come out to the same solution. So 2 squared is 4. The square root of 3 squared is 3. Plus, we have 2 times 2 times 6. So that's 4 times 6, which is 24. Square roots of square root of 3 times the square root of 2, which is 6. And then plus 6 squared, which is 36. And square root of 2 squared, which is 2. You'll notice here 4 times 3 is 12. 36 times 2 is 72. So really that simplification I did at the start is to help out with this middle term, because you're usually just going to get square root of 12 squared, which is 12, and the square root of 72 squared, which is 72. So then 12 plus 72 should give me 84. So my answer will be 84 plus 24 square roots of 6. Now next up, we have two binomials that look very similar, but the sign in between has changed. These are conjugates. And something special happens when you multiply them out. So let's go through the process. So 5 times 5, which will be 25. 5 times positive square roots of 7 is 5 square roots of 7. And negative square roots of 7 times 5 is negative 5 square roots of 7. And then negative square root of 7 times the square root of 7 is negative square root of 49. Now, I'll get 25. These two middle terms are actually opposites, so they'll cancel. Then I'll get minus 7. So 25 minus 7 is 18. So what's peculiar is that the radical actually went away. So when you have a binomial radical expression where you have square roots, the radicals will actually disappear after you multiply them. The reason why this is because of the difference of squares that's taking place. Whenever you have two conjugates, like a plus b times a minus b, when they multiply, they become x squared minus b squared, which is a difference of two squares. So if you recognize that they are conjugates, you can actually use that to more quickly get to your answer. So even before I would even try to simplify this, because I see that the square root of 8 does have a perfect square in it, I can actually just write this as 3 squared minus the square root of 8 squared, since I know that they're conjugates with a sign changing in between them. So when I simplify, I get 3 squared, which is 9. And then the square root will cancel with the square, give me minus 8, which is just 1. So it's much quicker if you recognize that it's a conjugate situation. And that is how you multiply binomial radical expressions.